So today I'm going to be discussing the 8 fallacies of distributed systems. I've been writing about these sorts of systems and writing these systems for the last 15 years. And until this day, I'm still constantly surprised on how different ways things can break. And it's probably why I'm still engaged in trying to build the perfect system. So as a high-level rundown of the talk, I'm going to cover each fallacy and a few ways to mitigate them if possible, and a few things that you should be aware of when you're designing these systems at your company or on your personal projects. Click there, go through. Give me a second. I don't have Keynote. There it is. Okay. So quick plug before I get started. I write a bunch about distributed systems and system design. Building one of the largest communities online around system designs and how we design systems and all the pieces that go into designing a system and its various components, everything from databases to queues. We're currently over 12,000 subscribers and engineers that are working on these types of works. If this is something you're interested about, I highly recommend you giving it a look. This is one of the talks that I give around distributed systems, which is kind of the kind of content you'd be getting from the thing with some deep technical dives and real deep explainers about system components that you may be using in your systems. So that's over. Let's get into the meat of the talk here. A lot of times when we start talking about distributed systems, we lose a bit of context when we're moving from one barrier to the next. So usually most places start off as a monolith because it makes sense for how these things work. And the monolith is essentially a big application that handles all the business logic. It contains everything that the application needs to do, even its various offshoots. And within that monolithic system, there's a lot of implicit things that we take for granted, in the sense that when you make a call to memory, the likelihood of that failing is quite low, and we take that thought or that ability for granted. So as you move into more granular systems like server-oriented architecture or microservices, these assumptions are no longer valid, and then causes us to rethink how we build these systems. And if you're not conscious about how you go from one to the next, you can lead to a bunch of headaches. And this talk is basically going to highlight a bunch of these headaches and how they're being done. More generally, the service-oriented architecture is very tightly coupled, coarsely grained, not too finely grained systems that have specific functions, and they work together as a unit to be able to work on and develop. And then later on, microservices were developed, which is very high grain. Things have smaller context, smaller usability. This became a thing more out of necessity when teams became larger, also for various other things and being able to scale out horizontally, but we'll get to those sorts of things later. So the first fallacy is you have to understand that the network, assuming the network was reliable, is not good, right? At any point, any piece of communication can fail. And if we need to provide a system with real ways to mitigate these failures, and ultimately it comes down to the retransmission, and that retransmission can come in many forms, right? Assuming that the network is always going to be there and it's always going to work reliably is one of the first fallacies of distributed systems. As you know, you've seen, most people have seen this on a smaller scale, not that big of a deal, right? You're running this service and you spin up a Docker container and you hit the web app and it's missing one of them. It's very simple to just kind of come in, turn it on and be okay. But when properly configured, these systems will continue to work and function. But there are places where these networks, even internal ones inside Docker, have these failures. And it could be a ton of things. It can be configuration, could be the network being down, could be tons of things. So being certain and understanding that the network is a core part of your infrastructure is important. More recently, I don't know if there are any people from Canada here, more recently we've seen something like this happen with Rogers. There was a configuration that broke and it took out all of the internet in Eastern Canada, which was one of the largest outages I think I've seen. And this was simply due to a configuration error in the routing tables for essentially the internet. And it took everything down from banking to billing payments, hospitals. It was quite a disaster. So assuming that the network is always going to be reliable is quite dangerous. And it's something that we really need to think about when we're building these systems. And the network may not be there and our systems need to be resilient. Now, in this particular case, core infrastructure was down, but understanding that this network isn't always guaranteed is quite an important thought to leave with. So let's say the network is down. What's the first thing your system should do, right? Most people just retry it, right? They turn the system on and off again and retry the simple request that you just made, which for the most part is a fine strategy. But how long do you run the retry for? where do you keep that data that's being transferred in between, right? Your systems have finite memory, and in a large scale system where there's receiving thousands, if not hundreds of thousands of messages per second, how do you keep track of all these pieces of data that you are pushing through the system, right? You think about it as throughput, right? You have a piece of data that comes in, you respond, and you go away, and that you no longer have to keep track of that state. And state is where a lot of these problems come into play, right? And mitigating state is a good way to how to solve these types of problems. How can I remove state from my system, right? So retrying is fine, but that also has its limits. So there is a clear pattern for solving this problem, and is using message queues like ActiveMQ, RabbitMQ, in Kafka. These systems use a store and forward pattern where we capture associated data with a specific request and process it later. Not all requests are possible like this, but there are a large subset of problems where things don't need to be done immediately. And as long as they're eventually consistent, this can be a great way to design your systems in order to ensure resiliency to network failures within your system, and ensure that the data that we need to capture, or the state, will be processed and moved through the system. These systems can also ensure single processing of messages. So depending on what it is. So let's say we're updating a row in a table to reflect some health data. That can be run a few times because the end result is going to be the same. Now, for other reasons, you may want to do that for efficiency in your systems, but for things like payments, you want to ensure that it's at least run once. And these systems with a little bit of effort can facilitate that type of work. The next fallacy is latency is zero. So the way I personally like to think of latency is strictly overhead that is done on every request. A message can be large or it can be small, but the latency will be unchanged. Unlike bandwidth, which I'll discuss in a second, latency usually has to do with the speed of light and the speed of communication, or the path or the distance a message takes between two systems. This is proportional with the distance of the system and the number of routing spots it has to go through. Latency can be ignored. Oftentimes, as you can see, latency can be quite small. But as I said earlier, when you're passing messages through a system, throughput is crucial. And if your system can handle at any time juggle 100 messages, and then you ask it to juggle 101, you lost one, right? And so you have to keep track of latency and understand that there can be back pressure if latency increases, and that back pressure will eventually cause some system in your distributed system to fail. So it's important to keep track of latency and where it's going, but it is everywhere. So here's a cool graph that I like to keep in mind whenever I'm building systems. I think most software engineers who are building systems like this should have a general reference for how long these things take. To me, it's basically, how can I reason about a particular request through my system, through all the parts of the system? We go everything from an L1 cache reference all the way through to a round trip packet message from California to the Netherlands, which is about 150 milliseconds, all the way down to 1.5 nanoseconds, right? This is a very popular graph and something that most software engineers should be aware of when we're dealing with systems. And these numbers are numbers that are important, so you can reason and do some quick napkin math to be able to resolve and calculate expectations for throughput to your systems. Latency is omnipresent. There's nothing that you can do to get rid of it. It is available in all communication. Even when I'm speaking to you, there is latency between the vibrations in my mouth is creating and when it's coming to your ears. And in this particular case, it's going through the network, which adds even more latency. So latency isn't something that you solve. It's something that you're aware of and account for. You can think of it more plainly as the time it takes you to go from, like, if you have a bunch of groceries, let's say you go into Costco or Price Club and you're coming back home, a game I used to play growing up was one trip only. So you try to load up as much as you can, so you only have to go back and forth to the car once. Now, the time it takes me to go back from the car to the fridge is fixed, right? I could go a little bit faster if I run, but there's a limit, and that limit is latency, right? I can load more things on and move back and forth, but the only way we can decrease that latency is to park the car in the house or get the car closer to the fridge. Yeah. So here's an interesting problem where latency turns its head, right? So let's think of a system where we have a car and we have the wheels for a car in the database. Let's say the relationship to car to wheel is one-to-many relationship. So let's say we're working in a system where we need to get all the cars, right? and we're trying to populate a system that shows all the cars and their respective wheels or wheel type. So there's two ways you can solve this problem. So we have one round trip for getting the cars, right? So we select star cars from cars, great. Then what we do, and this is an n+1 problem, where after that we go, oh, cool, we have all the cars. Can we please get me all the wheels for each individual car? So we're doing select star from wheel where car ID is block. So you're doing one full round trip for each car, right? That will multiply your latency by how many cars there are, rather than just going to the database. And there's several ways to solve it. You could do it with a join, so you get the data all at once from when you're asking for the cars, or you can get all the wheels if the table is small enough and it makes sense to be able to parse all that in one trip. So instead of having latency across all the cars, you have latency across the initial call. In the case that we do it with cars and wheels as separate calls, so 2 round trips, or we can do it in one big trip where we go, hey, give me all the cars and their associated wheels with a join in the particular first one. So the difference there is how many round trips you're making to your database. ORMs are really notorious for this, and it'll really end up becoming a thing where it'll really kill your system performance if we're not thoughtful about it. So to do a rough calculation for communication time, it's quite simple actually. You take the latency, which is omnipresent, plus the message size divided by your bandwidth, and your bandwidth is how much speed that you have on a particular line. So if you have higher bandwidth, you can send more bytes, or more throughput through the system, and it's kind of like a pipe. So that's how long it takes just to simply communicate. We're not allocating for any work on either end. It's just basically the time on the line. Another way to mitigate latency, and kind of going back to my example with the car and the groceries, is that you can move the data that you need to get to your customers closer to them, right? Physically. So this is the thing that a lot of companies provide, Cloudflare, Fastly, Akamai. These companies are leaders in providing content delivery networks. Content delivery networks are basically places where you store copies of the data that you know your customers will need in geolocated places near them. So for example, if I'm visiting a site in Korea, I would need, and I'm in Canada, it would need to then go all the way and do all the hops to get to Korea, make the request, and bring the data back. But if the person was running the service in Korea set up a CDN, it would have a copy of that data alongside the servers that I'm using in Canada, and I wouldn't have to make that full trip, and therefore the speed in which I receive the data, the latency, is quite improved. Again, this mitigates or lowers the time, but does not get rid of it completely. So with that, assuming that the bandwidth is infinite is also a problem. Assuming that you can continuously increase the data size on a channel without limit can be quite the mistake. This problem only turns their head when scale difficulties enter the conversation and specific communication channels hit their limits. So as you can see, the latency is the time it takes to traverse the pipe, but how much flow the pipe has is the bandwidth. And that bandwidth, I just noticed there's a typo on the slide there, so I'm gonna have to fix that. But the bandwidth is how much data can I push through the system. And you can think of it as the diameter of the pipe. I first ran into this problem accidentally when I increased the payload on one of our company's homepages by a factor of 100. This specific API, unbeknownst to me, was uncached and was loading a 3 megabyte payload on every page load request. No caching, no nothing, straight putting load on. And that was a very heavily trafficked homepage, and we saturated the pipes on that particular service. This also included a full round trip to the database for each payload. We quickly hit all the limits, and all our customers were kind of seeing this dinosaur page because the server was unable to keep up. On the bright side, you may be thinking, you just told me that I should try to take as much as I can for each trip and to reduce the effects of latency in your system. Now, these systems and things there's a trade-off between these two things, right? The more you load up for each trip in impetus of hoping to save on latency isn't always the smartest strategy. It may be in some, and it's a constant trade-off, and you want to kind of find the right balance for individual systems that you're running. If there are particular components in your system that require quite a separate bandwidth, I would advise to move it off into a separate network where you can keep track of those bandwidth limits. And it's a constant balancing act and monitoring your systems to understand how much bandwidth you have. It's also important to know, and if we were in person, I'd ask, how many people are aware of what the pipes between their network and their various systems are, and know what those limits are, and actually measure. It's an effort of measuring and really focusing on what we need to do in terms of ensuring that these particular systems are able to scale as we need them. What happens if we double our traffic? What happens if we triple? Right? These are the things that you need to think through when you're planning for resiliency when it comes to bandwidth. The next thing is assuming that your network is secure, right? I work at 1Password, so we're a security company. So this is always top of mind. We store encrypted copies of everyone's passwords in our systems, and they're encrypted end to end with several layers of protection outside of TLS. So it's important that you don't assume that your network is secure, right? The only system that you can truly trust and be sure that it's secure is a computer that's never been online and never been connected to the internet. And if you just want to see what that looks like, I suggest you spin up a node later today on Node and just put it on the internet unprotected and see how long it takes for someone to spike that box. Machines are being constantly attacked on the internet, and it's actually really interesting to kind of see the kind of attacks that are happening in real time. As you guys probably remember, most recently it was the what was that thing called? Log to fail. It was a bug in a logging library in Java, which caused everyone to be able to get root access on machines through an exploit in the library. If you would have went to this site that day, you would have seen thousands of machines trying to exploit as many machines as they could to get on them, to put on botnets and really get them going. If you go to that website, you'll kind of see basically a weather map of exploits that are happening online. Log4j, thank you, Faizan. And there's just a couple that I saw from yesterday, right? These are just two that are being run everywhere on the internet. One's a worm and another one is an SSH brute forcer. Taking security first stance is really important when you're designing your systems. Even just taking a pass to assess what places your systems could be vulnerable to for vulnerabilities and to harden them would be a great place to start if you guys don't have a dedicated security team, and it'll really help you guys harden your systems more, and it'll create a short list for you to just start doing these works. If anyone's interested in kind of how to do that, you can hit me up later, but this is a quite deep topic and it's constant effort of keeping and maintaining these things. But assuming that it's safe isn't a good one, especially when we're sharing data between systems out on public internet. So the next here bit is the topology doesn't change, right? Earlier, maybe 10, 15, 16 years ago, topology was a bit more fixed because it required a lot of physical effort. You have to rack machines, actually connect physical cables between them. So you could make the assumption that the topology wouldn't change that much. So then you could hard code things into machines. IPs wouldn't be bouncing around. But nowadays, with the growth of infrastructure as code, and with Docker, Kubernetes, and all these other things, you can rewrite the network at the snap of a finger, which then causes you to realize how we're going to communicate between these systems. How do we do service discovery? How do we talk to one another? Like the Facebook issue and the Rogers issue was a config that was pushed up that was wrong, and it knocked out one of the big routing tables for half the internet, and took Facebook off the internet, and took Rogers and all of its customers off the internet, right? If the network isn't set up in a way through their border gate protocol, it causes like mass failure in all our systems. So network is just as crucial. And in order to know where your system is going to be talking and how it's going to be talking, it's important to understand and reason about the network in a way that's independent of being hard-coded in the system. These infrastructure changes, as you can see, can be made quite easily. We need to build our systems so they're resilient, and tools like Console and Zookeeper are ways that you can engage in communicating services that are up and letting your systems be aware of the systems that it's able to communicate with and what health they're in. And with these in place, your systems will be a bit more resilient to these changes. And this is a constant effort, much like security. It's something that you need to manage and account for and actually test, knock out a good chunk of your system. And this is an area of engineering called chaos engineering. Basically, in a way that you kind of take off pieces in your system and you see how your system reacts. Is it able to recover? How long does it take to recover? How much failure happened in the meantime? And failure, that being said, is something that will always happen in distributed systems. I see a lot of engineers when they first start writing this type of code, and they want to have guarantees like they used to have in the monolith. Those guarantees are gone, and it's just a balancing act of being able to get to the closest level of assurance, right? There's these levels of nines that everyone uses to kind of measure their system's availability and reliability. But to me, is that knowing that failures will happen, and no matter how hard you try to make it available or performant, these errors will happen, and it's something we need to account for and be aware of. How does my system fail, right? That is a part of the engineering process as well, not just a happy path. There are no silver bullets here, unfortunately, and it's just a lot of work and a lot of hard engineering. This one was honestly, for me personally, one of the hardest ones to really grasp. There's only one administrator. This is essentially saying you can't control everything, right? Once you start working in larger teams, you're not the only one changing it. Like even on your laptop, let's say, right? You know everything about your system. You're the one who set it up. You're the one who added the configs, who tweaked everything just right, set up their mouse speed, keyboard configs, what displays are showing up where. So if a mistake happens there's no one to look at but yourself. But think about it. How many people touch your production systems? Engineers, operators, security engineers, infrastructure developers. There's so many owners in these systems, and being able to resiliently recover from this is part of that. And being able to know, hey, it's not just me running the system any longer. There's many owners, and I depend on others. If you were to just take a list of a particular system that you're particularly responsible for, and write down all its dependencies, the Linux kernel, and all the way up and down the stack, you'll realize that there's multiple people who have ownership of various pieces, and you're just a steward. And being aware of that is important. It'll also help you grow in terms of what you look into and what you have more interest in. But it'll also help you understand that being able to understand and how to recover from these things is quite important. Do you know everything there is to know about your system? One of these tools is being able to diagnose what's going on in your system to some high level. So this is a dashboard of Grafana. Being able to quickly recover from these, being able to use critical tools to save you hours in terms of debugging and figuring out what's going on in these systems. Appropriate decoupling is another strategy in order to decrease scope of responsibility, and having clear but loosely coupled contracts between systems is important. So I can make changes as long as I adhere to the contract that you guaranteed. I'm able to deploy and change my systems. This will also help overall system resiliency and flexibility. And if you limit the scope that each engineer needs to own, the better off your systems will be. But it's good to have a shared understanding of what these systems do, and these dashboards and systems like Grafana and other tools really help you get a high-level picture of what this looks like. Often this plus other things are the driving forces behind microservices, right? Expanding teams, expanding scope, various concerns of who needs to know what. Even configuration can be a problem of these types of systems. So having a properly managed configuration system is another crucial portion of running systems that would be, how you say it, important in ensuring that you don't succumb to this fallacy. Transport cost is zero. So this is another one that is only becomes obvious when you get hit with a giant bill. People often think when they send resources between systems, it's not really a cost. When things are small, these things are negligible, even almost free sometimes. But as these systems grow and your data sizes start to multiply, you're using up resources, and these resources cost money. The costs for optimizing transport costs between systems, in some cases may be useful, in other cases may not be. For example, back in the day, XML was quite verbose and large, and sending large data packets through that would be quite costly. We have better, more compressed formats now, like JSON, but they're really designed to be more human readable and can be a bit heavy, pun intended, compared to transfer formats that are ideally binary based, like gRCP and message pack, that can compress data and send them along the line a little bit quicker. often I see this type of cost come up when there's object storage involved, transferring data between two systems and supporting file transfers or database replication, and being aware that how you do that replication through what part of the network can be more or less expensive depending on how you do it. So I would consult the documentation that you have in your cloud providers, and if you're racking your own servers, you know how many NICs you have. So that's something that you need to account for your system, and not only monetarily, but also in capacity and throughput. Remember bandwidth and the bandwidth costs between the connection between these systems. So the cost isn't only monetary, but also in terms of resources. Now, doing this early can cause problems and cause other issues in the system, being able to quickly iterate and move. These things do have trace-off, but doing it earlier sometimes may create more headache than it's worth in the near term. And the last fallacy here is that the network is homogeneous, right? Assuming that you have a purely interoperable network can be quite dangerous in the sense that people, engineers solve problems, and I've written a shim or two in my day, taking one format and transforming it into another. In theory, everything likes to be super clean and everything needs to be to spec, but in the real world, it's far from it. And it's important that we understand that systems require a lot of work to keep them interoperable and communicating in a way that makes sense. Another way you can look at this fallacy is assuming that the network is equal bandwidth throughout all the portions of the system, right? Within our personal cloud or our personal network or on-prem system, we can ensure that the links between our system components have 10 gig NICs or 25 gig NICs. But on the internet, I'm on my cell phone in the bushes. I might be getting dropped down to 3G. You have to think about this experience throughout your system for all your customers, right? And depending on what you're doing, if it's mission critical or not, the work that you're doing, you have to be aware that getting this data to the system may put undue load. Imagine trying to download a 10 gig video on 3G, right? Some of these things are basically unfeasible. So that's another way of looking at this, and switching to the newest, hottest framework or moving to the newest tool, you may need to improve your systems from what they originally were to something new as the system changes. And obviously, as you keep doing that over a longer time and the system gets older, its interoperability becomes a big component of its value, right? And if done in a way that isn't backwards compatible, can lead to a lot of debt and complexity within the system. So being interoperable is essential, but how you do it is really the core thing here. Being in a way that is really smart. Stripe did a really good job. Their APIs are really forwards and backwards compatible for a very long time, because billing systems tend to not be rewritten quite often, and they're a system that needs to be reliable and consistent. So knowing that all systems aren't the same and not coupling your solutions to one aspect of a particular system and keeping them loosely coupled can really help save you a ton of time and headache for those of you that are working on these systems. And yeah, so that's more or less my talk on 8 fallacies of distributed systems. I think we have a bit of time here, but I will leave you with this quote. A distributed system is one which the failure of a computer you didn't know existed can render your own computer unusable. That's a quote from Leslie Lamport, and one that I really liked, in the sense that it really sums up kind of the world we're in and what we're working on. And it's important to really think through these things as the engineers that work on these systems. Failures will happen, but we really need to engineer our way to a place where we can really have some consistency in the systems we design and have them be resilient to change. Thank you. And, I'd be happy to answer any questions during the talk.
All right. Thanks so much, Mahdi. That was awesome talk. I think having those 8 points, so structured, I think it's just easy for us to understand. And yeah, I was curious about it too. I know some people were commenting on the graphics and the font and stuff. Did you make that?
So I work with a friend of mine. I'm not a particularly good artist. I did draw them in a way where I can render them and render the idea, and then they help me refine it so we can get a nice looking infographics people that can consume and really have some illustration to tie the concepts back to.
Yeah, for sure. I feel like it's just such a nice compliment to your talk. Like your talk is great, and like that the graphics just, I don't know, I just love looking at it.
Yeah.
It's sweet. All right, so I think we got one question here, but yeah, keep the questions coming in the Q&A. We got a little bit of time here, and I apologize in advance if I like don't pronounce your name correctly. So yeah, Najma said, blockchain, how secure is it and scalable? And you know, what are some of the design constraints?
Yeah, so blockchain, depending on what your flavor of it is, depends. So there's two main ones that I really consider like the ones that really innovated here, Bitcoin and Ethereum. Depending on the system, some of them are truly decentralized. Newer ones like Solana and whatnot are very distributed and centralized in the sense that everyone's running a node. Those systems behave more similarly to what we design in terms of how they communicate. They're all running separate nodes, but Bitcoin in itself is a giant database, and that's how you can think about it. Security-wise, I think they're pretty secure because everything's being done through asymmetric keys. So in order to be able to access that system, you need to have your keys in order to say, hey, I'm so-and-so. And Bitcoin specifically, and I'll just pick that one as an example, is a chain of blocks, and as records get written, those blocks are cryptographically signed and linked to one another. So you have one chain of data that's being signed and encrypted that's linked to the next one, and that's why it's called a blockchain. So you group a bunch of transactions into a block, and that block is then cryptographically signed into the next block, so that you know that this block came from the next one. In terms of security, I think Bitcoin's quite secure, but any system, if it isn't tried, Bitcoin's been around now 12 to 15 years. I don't know the exact date when it came, 2009, so I don't know, do the math. And there hasn't been any real main exploits. There have been some things, attacks against it, but nothing to undo it. But those things are only secure as the community behind them, right? In terms of scalability, they've had some issues in terms of throughput and writing these things, but that was built into the system to begin with. And those are the various design constraints that are happening there. Yes, that's correct. Ari, I can't pronounce your name, but you're correct. And yeah, those are the design constraints there. I'm not sure, Najma, if I answered your question, but there are some design constraints within it, but we'll have to save that for a Bitcoin talk.
Nice. All right, thanks for that. You got another question for Faizan. Could you talk more about the impact of different network topologies? What should I take into account?
So network topologies. So let me read that again. Can you talk more about the impact of different network topologies? Okay. So network topologies are essentially this. So let's say you have a load balancer that's at 10.10.1, right? Now your website is pointing at that load balancer. So, but let's say tomorrow that IP changes, right? That's a network topology change, meaning the way the physical network is structured has changed. Now, things like load balancers need to be consistent in the sense that they're receiving the data that's coming into the system, and that needs to be consistent. But if our system is a distributed system and all these independent pieces need to communicate with one another, it needs to know, hey, I want to go to the database. If the database moved in the network and its IP changed, it'll cause the system to fail, right? That's why a lot of times when you're in AWS, you get like a URL or a canonical URL to point to the database. So if the database, let's say there's a failover, AWS actually switches the underlying machines, but and then DNS gets updated and then it moves over to the next machine. So that is a way to make your system resilient to that sort of change. So hard coding IPs into your application is a mistake. The way I would do it is to have all your resources register themselves in some service discovery. And then when your application on boot says, hey, where are my databases? And it's able to get a real-time feed of that and to do checks on that consistently as things are happening within the system is important. Doing that in code is a balance, because once you have a connection established and you really need to ensure that connection continues to work with pooling and stuff like that, it gets quite a bit more complicated. But generally the strategy is set up a way to be able to discover these systems and then keep track of them and ensure that they're healthy. And if they aren't healthy, check back in. I hope that answers your question.
All right, thanks for that. I got another question from Aditya. Can we throw some light on the CAP theorem if it's not covered yet?
Yeah, so CAP theorem. So that's let's see if I can remember. It's consistency, availability, and partitioning. Partitioning, I believe, are the three correct. So the CAP theorem is essentially a way to ensure system reliability. So when you're looking at a database, it's one of two things, either a CP or an AP system. And it's essentially a trade-off because you can't have all three in CAP theorem. So basically, whenever you're working on a system, a database or a data store, that is a trade-off between those two things. So in a CP system, it favors consistency and partitioning, and in a AP system, it prefers availability and partitioning. And being able, so I prefer in the system where I have to balance between consistency and availability, I'm leaning towards availability, be up and be there. Being able to handle partitioning is another system there. There are various things, and there's a chart on the internet that is kind of wrong in the sense that these things are placed in different places, but it's actually a trade-off in particular scenarios. I'll try to share something after the talk about this. Same thing with PACE, PACLE. I couldn't speak to it intelligently right now. There's a lot of acronyms out there, but I will share some content around that after the talks. Just hit me up. My Twitter's there. I'll send you some stuff around that. And if you have any questions, I'll be able to go over that.
All right, this sounds good. Any other questions before we start to wrap up? Let me see. I think we got something. All right, we got one more from Nathan. Let's take this one. So curious your thoughts on edge functions with CDNs to reduce latency, and also database structures like, what is this? Cockroach DB?
Yeah, it's a database.
That right? Yeah, that serves transactions close to the user. Yeah.
Yeah. So so there's two things there. Yes, I think edge functions are great. They're still new and they're still figuring out cool ways to deal with it, but I feel a lot of people have been taking great advantage of these things. I think they're a great way to help keep data local to a particular system. They're really useful in caching, where you can keep the caching local to the customers that you need. I think it's really cool. But there are other downsides on how you do how you clean up the cache or manage the cache, and also being able to reason about what's going on the edge. But I think it's a great technology. I think it will help a lot of problems that we're having in terms of keeping data distributed, especially with the coming up of WASM and whatnot. Having these things run on the edge is a really cool thing. But I haven't seen a really killer use case for it just yet. I think a lot of people are just playing around with the technology. I think we're still waiting. It's a solution, kind of still, in my opinion, waiting for a problem. There are some unique cases where it becomes very useful. Kind of keeping. I know Slack makes heavy use of this. Going reading about their architecture might be a good thing that you do. The next part here was database structures like CockroachDB that serves transactions closer to the user. So CockroachDB is a serializable distributed database that's built on, I think it's based on Postgres. It's actually quite awesome data store. And you can have it's multi-write, so you can write to anyone and it keeps it in sync. And they have a lot of great capabilities in this database. And for a database, for the most part, I think having it being distributed, DoorDash is a big user of this database. If you want to go look into what they're doing with it, it's quite awesome. They're able to sustain, I think, over 300,000 requests per second with Cockroach distribution. So they have networks and nodes all over the world. And depending on where you are, you'll go to the closest one that's near to you, and you're able to serve your request. And let's say then you travel later to another part of the world or another part of the country, you can query that same database and we'll have the transactions you committed somewhere else. CockroachDB is awesome, and there's a lot of cool things that are there, but it is a serializable database, meaning functions are run sequentially. And the reason why you have so many nodes is so that you can do that. They're not in theory, they're run sequentially, meaning that one query cannot affect another until it's complete, but they are run concurrently. So you do have to deal with failures. So let's say you make a request and it fails, you have to build in retries into that database. Otherwise, you'll have a ton of them that fail. across the board. I hope that kind of answers your question. I think it's good if you have that kind of problem.
All right. We've got a question here, but Mahdi, you can decide if it's gonna take a while. Then yeah.
No worries. I can quickly wrap it up here. Best way to deal with random failures in a non-transactional series of operations. So this is a big one that people run into immediately when they're moving to distributed systems, right? There's no such thing. There are some systems that claim this, but there are no such thing as distributed locks, meaning having a distributed system where you kind of lock everything in place. You can do something called a two-phase commit, which allows you to do one portion of the work, and once that's done, you unlock the rest of it, and then it's able, so allows you to get some consistency between the two. By doing this, it decreases your system's throughput. So if you have a system where you need high throughput, then this becomes a problem. This is a deep topic. Hit me up after. I'll send you some documentation on what my thoughts are on it. But for the most part, it's a hard problem. And my view on this is store what you can and then move forward, right? In the sense that put in a system like a queue where it processes the system in a consistent manner. And then once all the work is done, then try to lock and send up the updated value once all the work is done in the system. But that's a deep topic, and I'd have to know more about what you're trying to do to help you really there. But it is a problem that people run into quite quickly. I would see if you could break up the system into known parts and then compose all the work later on.
All right. Well, thanks so much, everybody. And thank you so much, Mahdi, for taking the time to share with us today. Yeah. And let me just, do a little wrap up here. So yeah, I also put the Mahdi's Twitter on the chat, so you can just click on it and connect with him. Yeah. And Mahdi, is there any kind of just final remarks, encouragement for our friends here before we go?
These things are really hard. It takes a lot of work. And I would look and read as best you can about these systems, talk to people that you talk about these ideas more generically, like talking about these things. Engineers always rush to writing code immediately. Talk about these things and the problems that you're going to be facing, and then address them all individually, right? And if you break the system into smaller parts, I think you'll have much more success, right? Trying to take it all on at once can be quite daunting, but if you break the problem, and most problems are composable into smaller sets of problems, solve those individually and work your way up is what I recommend. And keep plugging.